Today we're going to learn how to use the Autobox Method 5 software, the automated Method 5 software. You begin by either clicking on a shortcut to the Meter 2007 software or by hitting Start and find a shortcut there. The history will pop up. The default history for basically historical tests that have been done on other different power plants are stored in here. You can see we have a list of different tests that have been done in the past. Jamestown, AES. So if you are working at the same site and can use one that's already pre-configured for that, perhaps like doing a flow test at Indian River Unit 1, you could select that from our list. If not, you would do the default blank history, and in this case it's called Meter 2007, and we're going to do that today. So we'll load our blank project into the... Now each set of software, each instance of this software basically can run two boxes. So each time you start the program, you can operate two Method 5 boxes with this software. This one being the A side and this one being the B side. So these are two separate independent boxes that can be together or independent completely. Can be at two different locations. Basically, they're just two separate boxes. If you were to click on the link again, we could open up another instance, but you'd want to select something different. So in this case, we'll just name this Test 2. And we'll hit load. And I made a mistake in the first one. You really don't want to use the Meter 2007. That's just the default setting. Basically, we want to create a new one. So in this case, let's go back and we'll do this again, and we'll call this Test 1. So here we have basically 4 Autoboxes that we could set up. Now we're not going to set up 4 today. We're just going to set up 1. But I just want to show you that you can open up multiple boxes. So if you were running 6 simultaneous tests on this computer, you could open up 3 different screens and name each one something different. And so now you would have 6 control screens for 6 individual Autoboxes. So we'll just close 2 of them and go back to our 1 test. And I resize the screen so we can see everything that's here. Now the first thing you're going to want to do is go in here and click on communication, and this is important because you need to communicate with the box, so you need to configure the communication in order to actually read from the box. So we hit setup and communication. These settings are constant settings. They match the PLC in the Autobox, so they're not ever adjusted. The prefix is never adjusted because we're using COM ports. And here we have the port. The port is either the USB or serial port that's being used to communicate with the Autobox. So in order to find that out, typically we're plugging in a USB to serial adapter, which is a small adapter that would plug into a USB port and then connect to our cable running to the Autobox. So we need to find out when you plug in your USB adapter, the computer generally assigns it its own number. So you would go in here and you go to computer, and if you right click on the computer and hit properties, you'll get to your device manager. Different operating systems have different way of getting there. And you'll click on ports, and you'll see I don't have a USB port attached at the moment, but if I did, it would show up here. Give me 1 second, and I will plug one in, and you can see what I'm talking about. We have a multitude of different kinds, but I have one right here I'll plug in, and the computer will assign it a... So in this case, it assigned it to USB to serial bridge COM port 1. So that would be the port that we would need to enter in here. And as it is, it's entered as port 1 right now. And then you would need to look at the Autobox itself to find out the name, the number for the Autobox. And if we were configuring this first system, meter box A right here, to be, say, number 4, you type that in. And the second one, let's say, would be meter box 6. Now the timeouts is really just the time in which the signal is sent to the box and returned before it times out and gives you an error. Typically 300 works fine, but sometimes you have to lengthen this out a little bit, especially if we're working wirelessly. It takes a little longer to get the signal back, so you change that to 600 milliseconds. And then we hit OK, and right now you'll see PLC error on both these, meaning they're not communicating. Later on in the demonstration we'll actually connect up to a box, so we'll see this work, but in order to get the PLC to communicate, you need to reboot the program after you set the Autobox number. So we would have to cursor down and find our file history that we've created, in this case test 1, and we would reload that program back in, and because I don't currently have the Autobox connected, it's still giving us a PLC error. But if it was properly connected, this PLC error would disappear, and we'll show that in some other next step here. After we get through configuration, we'll show you that in the actual operation of the Autobox. So the first thing to do is to actually set up your system. And there's two main screens. One is the system settings. This is the primary one to designate which what you're doing here, and you can see down here we have different modes of sampling. We have method 5 mode, we have method 6 non-isokinetic test, and we have 30B carbon tube sampling, and we have 201A PM10 sampling, method 4 such as moisture, and we have flow and 3G and 2F, or I'm sorry, 2G and 2F for 3D flow. So we'll set up a method 5, a simple method 5 train today, and it's just going to be a single train, not doing any paired trains or duplicate trains. And so you can see for meter box 1, it's set as the one we're currently setting. So not sure what that is, but we'll just close that. So right now we have our minimum and maximum scale for our delta P, which is our flow, our stack flow. Most flows you can set it to whatever you want, but I typically set mine to 3, and my delta H I usually set to 3 also, and vacuum I always keep at 30. And one would need to look at the raw master factor adjustment on the Autobox. Some of them are 1, some of them are 0.98, and a lot of them are 1.39. In this case, we'll put in 1.39 off of Autobox 4. That is right on the box. It's a constant number that's always used. It's basically, it has to do with the hardware, so that number remains constant for the box. I don't know why this is doing this, but we'll close that one more time. So then we have our probe heater set points. In case of method 5, we heat both the probe and the filter for an out-of-stack filter arrangement. So you need to know the methods, but you can set your filter temperatures. And we also know that our scale for a standard method 5 is going to be 0 to 10 inches of water. That's the device that's installed in the method 5 box. And that's your default reading here for the method 5. For our 3D boxes, our scales are either 0 to 5 or 0 to 0.5, depending on which transducer is actually mounted in the box. So in this case, we're good for box 1, and when you switch to box 2, those values will be saved. So we'll set this. We're just gonna close that again. Set our delta H and delta P to 3-inch scale, and we'll set our box factor for number 6 to 1.39 and hit OK, and you can see here your scales then adjust accordingly. Delta P up here and your delta H right there, and your vacuum gauge at 0 to 30 inches. Once that is set, we need to configure our preliminary data, which is descriptions of our test. Gives it a general test, so we're going to call this we'll call this inlet particulate. Say we're doing an inlet-outlet test, and this could be outlet particulate. It's basically just a description of where we're testing. The client, say maybe NRG. And these are for the 2 boxes. Say we're testing unit 4, and test location would be, say bag house, inlet, and stack. Our method EPA, method 5, EPA, method 5, and we have a test number, which basically each test is a set of 3 runs. So in this case, we're going to do 3 runs at each location, and so we would be on test 1 and run 1. You can enter your job number if you know it. Say 9025559. You are I am the operator here. Can run a 60-minute test. You would identify the number of ports and points, which could be done here by simply clicking on this, and your sample point calculator will pop up. We have a circular stack, and it's 180 inches. This particular points per diameter is for your stratification test for doing SEMS work. This is for both SEMS and method 5 here, this particular screen. So if you were going to do 6 points here, you would see your SEMS gives you to do your SEMS stratification, which is a different method, but you would get your 6 points here. If you had a port depth of 8 inches, but the main thing for stack particulate would be to enter your dimensions for your A and B dimension here for the stack. Let's say 900 and 2,000 feet, and we have 4 ports. and we are doing a particulate test. Here you can see we would be calculated to need to do 12 points. This is total number of points, so that means that you would need these 3 points per port. If you're doing 4 ports, you would do 3 points a port. So that would be your 3 points to mark on your probe, 15, and that would include your port depth of 8 inches. If you change that to 0, you can see this changes. Now you just have your total port depth, assuming you're from the inside of the wall. And you click OK, and you can see here that it updates it to say 60 minutes. Number of ports is 4. Our number of points is 12. Our stack diameter here 180. Length and width is for square ducts. Port depth is set to 0. Gives us our stack area. Circular stack. Method 5D is a different type of test, and we'll go through those in a different module. And our upstream, downstream. And then we get to our Autobox ID, which is the same as AB4 in this case, and AB6. For this box, it matches the, when we set up these for the communication, we identified that the first box was 4 and the second box was 6. We'll click on that. Sorry about that. We'll put in our delta H at 1.895. You get this information directly off the Autobox. It's from the calibration. And so you'll get your delta H at and your meter factor. I'm just guessing here what they are. Each current calibration would be, for that box, would be printed on the front of the box. Pitot coefficient is always 0.84 for an S-type pitot tube. Barometric pressure, you would use your handheld barometer to read that and enter the current day's barometric pressure. Estimated moisture, you would enter in from previous data. Same with the O2, CO2. You would enter in previous information. Here, nozzle, you need to size a nozzle. You can select from a list of nozzles, and if you find a nozzle that you can see here, you can cursor through and it gives you the different nozzle sizes, and metal versus glass nozzles. There's some glass, some are in Minnesota. So let's select, say we select this one. Or you can manually enter in the nozzle 2, 0.247, let's say. Be careful to make sure you don't have any typos. And probably the most important thing is this is your data file that saves your data. And if you don't enter a data file name, it will not save. So let's call this inlet PM NRG, outlet PM NRG. Now static pressure, you can enter in a constant static pressure, 0.2, and it will use that constant static pressure like a preliminary measurement. Or on some of the boxes, they're equipped with a static pressure to continuously measure static pressure, which is why you would flip that switch and you see it disappears, and that's because it will use the actual transducer. It will actually read the data just like it would real time. With flow, it'll actually read the static pressure in real time, and it will display our value right here when we actually read one. If the the probe is plugged into the negative side, you would leave this negative, and if it was plugged into the positive, or if so such that the stack was exhibiting positive pressure, you would click on that and it would log the data as a positive reading. Most stacks are negative, so if they're plugging it into the negative tap, then you would leave that as a negative. So what we have here then is, since your data is updated here, you have your inlet particulate identified, and this information is identified for both boxes. We have our delta P reading. When the probe is inserted in the stack, it will start to record a reading here, of a flow reading. You can use these two buttons to enter them both, and that opens up a three-way valve which allows the pitos to be zeroed, and if they're not zero, then you can press the 0 button to re-zero the manometer, and then shut this off, and you can see the 0 becomes disabled. Here is your delta H, and if the box is off, you can also zero that. Typically these do not need to be zeroed. They're usually within 0.01 of or at 0, and so they typically don't need to be zeroed. If they're anything greater than 0.01, you might want to zero it. Here's our timer. Timer can be turned on and off manually here, and it will start to count. Most of the time we don't actually use this button. We usually do it in conjunction with opening the sample valve. This is strictly just the timer. So if we were going to turn on our sample pump, we would turn that pump on, and one of the things to be sure of is that the pumps are sometimes cold and they don't start up, and we usually need to confirm that the pump is on. One way to do that without anybody looking at it is to turn it on and turn this sample valve open, and if the sample pump were to be on, it would immediately peg this up at pass 3 and start drawing a sample, and then you would know that the pump is on. Otherwise, you need to have somebody confirm that the pump is on, because if you turn the pump on and it's too cold to run, it will sit there and heat up and overheat and potentially burn the pump out. But once they warm up, they turn on and off, and you can always tell. It's usually only a problem in the wintertime. When you turn on your pump and turn on the sample, it automatically turns on the timer here. So that's typically why we don't use the timer on-off button, because it's integrated into the sample on-off. You turn that off, it turns off the timer. And then you would need to reset the timer over here at the end of a run. So here we have our dry gas meter reading. Reads 0. Right now, if it was connected to the box, it would be reading the reading off of the box. You can press this button, and while that button is pressed in under and says reset on and is red, the box meter reading will always be 0. It only will start to tally or total up when you turn the reset off. At that point, then the meter reading will start to increase as long as there's flow going through there. The meter reading is expressed in cubic feet and in liters and a liter per minute rate. And you can see here that the Autobox data is entered in here. Shows up from our preliminary data page where we entered that data. It shows up here. Over here we have our alarms. Alarms are what warn you when you have problems. So you turn your alarms on, and it will tell you if you have temperature problems or disconnected thermocouples. It would highlight these in red, and we'll see that shortly here. We'll connect up the We'll connect up our Autobox to a live box and get readings here shortly. Auxiliary, when you turn auxiliary, that turns on the auxiliary power to both the filter box on the stack and also to the auxiliary outlet on the Autobox itself. Pump is a small sample pump used to collect O2 CO2 data. It's built into the Autoboxes on some of the models, not all of the models. So only those models that have those pumps in it will actually turn on and provide a small sample for, say, collection of O2 CO2 into a Tiddler bag. We'll get into this here, but essentially this is your sample control valve, and if you want to increase sample flow, sample collection rate, you would dial this up, and you use this slide rule to determine how much it'll dial up, 10 being the maximum, 1 being the minimum. So if you have it set to a 1 and you click on it, it'll only turn a very small amount. Typically for method 5 tests, kind of a intermediate amount would be 4. So you would hit the button here and the valve would open a moderate amount, and if you hit this button it would close a moderate amount. If you were wanting to dramatically open the valve, say at the end of a test, you want to dial it way down because you had excessive vacuum during your test, you would maybe turn it to an 8 and then dial it way down, meaning slow the sample rate way down. And this is what's used to control the sample rate during the test. Then we have all of our stack temperatures, probe temperatures, filter dryers, the impinger out temp. We have meter in, meter out temperatures, and we have an auxiliary temperature, which is the number 5 thermocouple. Probe, you hit the probe on button and it will start heating the probe. Probes won't heat if it doesn't record a temperature here, but when it is turned on and it is heating, this little indicator button will turn red, indicating that the probe is in fact heating. Same with the filter on. This indicator would turn red and indicate that the filter is heating. You can turn them off after your test to allow the guys to change the filters and to brush the probe. Here is our nozzle diameter and our test number, run number. Currently the estimated the estimated ISOs per point does not work. It's not finished yet, but the overall isokinetics show up here, and it gives you a real-time isokinetic reading during your test, letting you know how you're doing during the test. We obviously are aiming for 90 to 110%. It should fall into that range. If it isn't, there's something wrong and need to stop the test to determine what the problem is. Typically when you start your test, initially there is a big surge of sample that goes into the system, so you get high isokinetics, 130% initially, but it'll quickly drop down to near 100 shortly. We have your point and port indication here. It tells you what port you're on and what point you're on. In automatic mode, the person would be told via the next point button, a signal would be sent to, which would show up as a red indication here that it is time to move your probe to the next point, and the button would be flashing and beeping up at the stack, and when they press the acknowledge button, the light this little indicator would go back to gray as it is now, showing that they did move the probe. Of course, here's your all your preliminary data that we've entered in here, and that's used in this overall isokinetic calculation. We have our vacuum gauge here that indicates the current vacuum. Clearly, if we're maxing out at about 25 inches of vacuum, you have a plugged up system. Your filter's plugged and would probably need to change the filter. And in the opposite of that would be zero vacuum, meaning you're likely not sampling anything. It's either got a big leak or your pump isn't running or something is wrong. So they will. That's just briefly how you set up your system. We will continue on with a demonstration in the next module on actual operation. We'll connect up to an Autobox and you'll see how the system actually operates in real time. Alright, that's it for now.